Alright, hell yeah. So what we have here is a JEE Advanced. I don't even know what that means. But people are like, hey, you should do one of these problems. And most of them I can't do. There's no way. But this one's right up my alley. You know what I mean? It's a disc, and it's got a rock attached to it, and then it spins, and then at some point the rock flies off. You know what I mean? And so I'm just going to draw smaller pictures. And so let's say like it's rolling this way, and the rock like flies off right there. Well, look, check it out. It's just going to go straight up, straight. Well, no. Even in this, like it would go straight up. It wouldn't go straight up, straight down because, hey, this spinning disc does have some velocity that way. Cool. So the second it let go, it's got a component that way, and then it's going to go straight up. So hell yeah. So, you know, due to vectors, it's going to be at some sort of angle. So yeah, there's a lot of places. The only places that make sense for this rock to like maybe leave would be probably in the upper hemisphere. So hopefully that happens. You know what I mean? Hopefully the rock leaves somewhere. I don't need to say it twice. Okay, so hell yeah. And then we're just gonna, you know, I don't think you need to know anything about radians per second. You know, well, you kind of do. What we're going to use is the axioms that, hey, radians per second. This is angular velocity. Hopefully I'm saying that right. It feels like there's like 3 ways to say it. And then alpha, I'm sorry, alpha is angular acceleration. It's radians per second, and if you do it this way, per second, it makes more sense because it's going to be the change in velocity. You know, this is synonymous with velocity. This is synonymous with acceleration, but it's radial velocity, radial acceleration. But you do have a change in angular velocity. So literally, this is change in w, change in time. Hell yeah, or dw. dt. You know what I mean? It's the definition of it. And then radians per second, well, does that mean that it is also, you know what I mean, kind of like synonymous? Could we do this? Could we be like a change in radians? Do we just do an angle for that and then change in time? So that would be a d radians dt. Cool. And radians is an angle. And then, so yeah, so the other one is just radians. You know what I mean? This is radians. And my axiom, it works great because no one knows what the hell a radian is. And so I just say, hey, radians, radian times radius is something normal. Cool. And then radians per second times radius, hey, is also something normal. And then radians per second times radius, hey, that's also something normal. So in this case, the something normal. Well, let's go to the easiest. Sometimes you'll have to go to the easiest case and then fill in the rest. But radians per second, this is going to be our omega, times radius is velocity. That'll probably be the easiest one. Radians per second times radius is something normal, and that's velocity. You know what I mean? Kind of tangential velocity. So if I have hell yeah, and then it's spinning with angular velocity, and then this point, you know what I mean? It'll have a tangential velocity, velocity tangential. It has no velocity that direction. You know what I mean? That's 0. That would be, anyway, the normal velocity, maybe. And so then we have a radius here, and then this velocity tangential, what did we say? It's radians times radius. Cool. And then we do need to know what the hell a 1 radian is. You know, what the hell is 1 radian? Well, it's about 60 degrees. So if you split a circle up into about 3 pieces, you're pretty much there. But radians is 2 pi, which is 6.28. You can remember 6.28 really easily because pi is 3.14, and it's just double that. See how the 8s and the 2s and the 6s. Hell yeah. And so yeah, it's about 60 degrees. It's like 57.3. And we'll even go to our calculator, switch to radians, and then just do, I don't even know how you do 1 radian. You'd have to go like the sine of 1. Oh, damn it. I don't even know what this, no. I don't even know what I'm talking about. So anyway, so we'll have to get back to that one. You know what I mean? People don't know radians. So yeah, anyway, so it's 57.3. For the life of me, I don't understand why I can't get that. Oh. No. I remember why. So what the hell a radian is? So radian times radius, what is this? This is arc length, typically S. And so what that means is if we take the radius and then measure it with a string, and then drape that string around this circle, we'll get to there. That's as far as we'll get. And if we have about 6 of those strings that are cut to the length of a radius, we'll basically get around this circle, but we'll be this 0.28 short. You know what I mean? And then so, hell yeah. So now that totally answers the question of what 1 radian is. Because there's 6.28 radians in a circle. There's 2 pi radians per 1 circle, you know what I mean? And then so you could say this is also 2 pi radians per 1 revolution, you know what I mean? And then you could say, well, when we want to figure out the degrees, so we want to go, there's 2 pi radians, and then, no, I'm sorry. We want to know what 1 radian is. So then we use factor label method. Well, we must have to cancel radians downstairs. So we do 2 pi radians. Hell yeah, radians cancel. And then what the hell is 2 pi radians again? It's going to be 1 revolution. I mean, you could do 1 revolution up here, or you could just do 360 degrees and get on with life. But we can also do another 1 revolution is 360 degrees. So factor label method is just like, hey, you know, label 2 things that are identical. 360 degrees is 1 revolution. 1 revolution is 2 pi radians. And then you can start canceling stuff. And then you get 360 divided by 2 pi. And for the techies, this is just 180 divided by 180 degrees divided by pi. You know what I mean? Half a rotation, half a circle, 180 degrees of a circle is a pi radians. It's 1.57 radians. 3.14, that's also, you know what I mean? Hey, 3.14, what's divided that by 2? Well, it's about 1.5, right? But then it's 1.5, and then what's 14 divided by 2? Bet you didn't know that. It's 7, you know what I mean? So 1.57, that's a real easy way to remember what the hell's pi. You know, it's 180 divided by 1.57, and now you know. Cool. So, and then if you do this, 180 divided by pi, you get 57.3. So it's just, you know, it's just good to know, hey, it's 60, it's 57.3, it's actually 57.296, you know what I mean? All right, so moving on. Now, radians per second, well, this is how much the angular velocity changed, you know what I mean? So if you have a saw that's stopped, and then a moment later, you know what I mean, let's say 1 second later, it's going 6,000 RPM, rounds per minute. What's the angular acceleration? So this is always one that I do, and you know, it's going 0 RPMs at time 0, and in 1 second it's going 60,000 rounds per. So the units are the equation. So we have change in radians, change in time. Well, change in time is 1 second. Change in radians is going from 60,000, you know, 0 to 60,000. So it's basically just 60,000 revolutions per minute times 1 minute using factor label is 60 seconds. And then what's 1 revolution? 1 revolution is 2 pi. So right here we got 6,000 divided by 60. This is rounds per second, revolutions per second. It's just 100. You know what I mean? Isn't that bizarre? You're just like, okay, my saw goes 6,000 rounds per minute. And for whatever reason, I don't think people put 2 seconds into thinking, well, how many revolutions per second? Well, it's 100 times per second. And that's pretty amazing. Your saw blade is going faster in circles than your lights are turning off and on. The hertz of your lights is 60 off and ons per second. And this thing's passing go 100 times a second. So the frequency is a little bit bigger. Alright, hell yeah. So, you know, 10 minutes, another 10 minutes on the clock, we might get to the problem. But we need to understand what the hell, you know, definitely angular acceleration. It comes up in here. And then we also need to know, so that there you go. So what was the, so we got 6, so that's going to be 100 revolutions per second. How many radians? So even just right now, you can just mentally, if there's 6 radians in a circle and I'm doing 100 revolutions per second, well, I must be doing 600 radians per second. There you go. You know what I mean? Just having that, like, how many revolutions per second? You know what I mean? You know, the next time you turn on your drill, is it 1,000 rounds, revolution? Is it 1,000 RPM? Well, how many revolutions per second is that? I mean, just do a factor of, you know, divide it by 100. Say there's 100 seconds in you know what I mean? So you're going 10 times a second, you know what I mean? Hey, there you go. So just a normal drill, 10 times a second at max speed, and there's 6 radians per revolution. So you're going 60 radians. And, you know what I mean? 1,000 divided by 60 is a little bit more than that, times 6. You're going 100. You're going 60 to 100 radians per second when your cordless drill's going full. Okay, so hell yeah, let's do this one again. 6,000 divided by 60 times 2 pi, and we're going 628.3 radians per second. And guess what? We're doing that in 1 second. We're going from 0 to 628.3 radians per second. So the angular acceleration is 628.3 radians per second, or written as 628.3 radians per second squared. Booyah. And so now, okay, so now I think we're fully prepared to do this. So we have at time, you know what I mean, let's get a new sheet of paper. So at time t is equal to 0, a disk of radius 1 meter. You know what I mean, let's get some, you know, anytime you see radius, holy Toledo, you got to mentally think that, okay, this thing is 2 meters in diameter. You know what I mean? So that's crazy. What's a meter? I always say 40 inches. You know what I mean? 40 inches in a meter. So that's 80 inches. This is a huge disc. 80 inches. Isn't that like 7 feet? Isn't that 7.5 feet? 80 divided by 12 is 6.5 feet. I apologize. But yeah, it's, well, duh, it's 1 meter. Yeah. Anyway, but yeah, it's 80 inches. It's 6.5 feet in diameter. Starts to roll without slipping on a horizontal plane. So we're going horizontal, and it has, but it starts to roll. You know what I mean? So sometimes they don't spell it out for you, but velocity initial is 0 meters per second, and then it starts to roll. It's on a horizontal plane, so maybe something's causing it to roll. Cool, you know what I mean? Maybe it's got a little motor on it or something. But now it's got some angular acceleration. So hell yeah, and the angular acceleration is 2/3 a radian per second. So hell yeah. So now we know what we're cooking with. You know what I mean? So we're gonna start here. We're gonna, hey, this is 1 radian, 2 radians, 3, 4, 5, and then 6. And then so in 1 second, we're gonna be 2/3. You know what I mean? So well, what is that in degrees? So we're this was about 60 degrees. So about 40 degrees. Cool. So in 1 second, we're there. No, that's not true. I apologize. Oh, yes, yeah, so this is where you got to be careful. So in 1 second, our velocity went from velocity of 0. I apologize, but you think of it as velocity. Velocity is 0, but its angular acceleration is 0. We're 0 radians per second initially, but then in 1 second, our angular acceleration, t equal 1 second, is equal to 2/3 a radian per second. So that means here's a good one. A car. You're going to start out going 0 miles an hour, And in 1 hour, you're going to increase your speed so you're going 60 miles per hour. But you started out going 0 and you slowly increased your speed to 60. And guess what? You drove for 1 hour. How far did you go? Well, you need your average speed. And your average speed is right down the middle. You were going 30 miles per hour for 1 hour. At the end of the day, that's how fast you were going for 1 hour. So the same thing with this is true. We were going 0 radians per second, and now we're going 2/3 a radian per second. So our average, in that first second, we're going 2/6. We're going 1/3 a radian per second. So that's our average speed. And if we went, so if we're going radians per second, here's the units, and then we travel per second, what do we do to these? And I know it's super basic, but the units are the equation. If I want to know how far the distance in radians we traveled, and again, this radians is like, hey, the angle. Like, I want to know, you know, like I'm doing 360s. Did I go 90? Did I go 180? Did I go 270? You know what I mean? And we can figure out how far, you know, the linear distance later. But yeah, so that's what we're trying to figure out. We're trying to figure out this angle in radians. So we're radians and then time, and then we have, anyway, but it's better to do this. Units are the equation. What do I do to get radians? Well, radians is already on top, so I just multiply these together, and I'm going to multiply 1/3 radians per second times 1 second. And I went 1/3 a radian. So in that first second, I went 1. So if this was a radian, I went only 1/3 a radian. All right, now let's figure out, you know what I mean? We have to do this problem in a normal amount of time. And so it says later at time t. This is where they're interested in. The stone detaches itself. So we're going to use kind of this, you know, loopty-scoopty process on guess and check. And it's the integration process, but it shows you it just really nicely, you know. And it shows you kind of what's going on. So we got the square root of pi. And so, cool. So we're going to do a time of only 1.77. So in 1.77 seconds, that's when we're interested. And let's just say we did it in 2 seconds. You know what I mean? You know, that's close enough, right? So that's the thing. The first thing about hard problems is we just kind of want to get get close as possible in the simplest way, so we make the least amount of mistakes. All right, so now we're here, and in this next second, I mean, we're already going 1/3 a radian per second, and in the next second, guess how fast we're going to be going after 2 seconds. Well, our angular acceleration is 2/3 a radian per second. And let's write that again. Angular acceleration is 2/3 a radian per second. Written like this is your change in radians per second every change in time. And our time is just 1 second. If our time was 2 seconds, you know what I mean, we figure that out. And our angular acceleration is constant. So after we do this 2 seconds, we can just go back and do the 1.7 and then be pretty much just on course. But we're just going to guesstimate 2 seconds. Our new velocity after 2 seconds is, and I'm not going to write it there because it's 2/3 a radian per second. So now we started, let's say we started our trip going 30 miles per hour, you know what I mean, at the stop sign, you know, we got up to 30 pretty fast. And then from that point on, over the course of the whole hour, we decided to go from 30 miles per hour, and I'll do it like this with our graph, from 30 miles per hour to 60 miles per hour. So now the question is, in that 1 hour, how far did we travel? You know what I mean? Well, we traveled 45 miles. You know what I mean? Or I guess what we asked before is, what's our average speed? If we started at 30 and we slowly ramped up our speed to 60. All right, hell yeah. So our average speed is going to be 45 miles per hour. And so you can just say, hey, for that 1 hour, we were just going 45 miles an hour. So if you want to know how far we were going in that hour, we went 45 miles. Cool. Just like the previous, going from 0 to 60, in that our average speed was 30, and we went 30 miles. Cool. So now we're going from 1/3 a radian per second to 2/3. So to find radians average, you just add them and divide by 2. So we got 1/3 plus 2/3 divide by 2. And I think the simplest way to do this is I don't even know. Doesn't this just add up to 1? So we got 1 divided by 2 is just half. Cool. And that's bizarre. 0.3 plus 0.6 divided by 2. Yep. So yeah. 1/3 plus 2/3 divided by 2. Sometimes you just got to go a little extra just to make sure you're not going to make mistakes. But heck yeah, we got a half a radian per second. Now this is our average speed for that second. So in that second, we're going to go a half a radian. So we're at a third a radian, 1/3 plus 0.5. And now we went 5/6. So if these are third radians, this is sixth, and now we're at 5/6 a radian. Cool. So 5/6 a radian, and this is our angle. You know what I mean? And this is the angle that the rock's going to fly off. And it doesn't matter what direction. I just chose that we're going to roll this way. That doesn't matter. The question says when it flies off from the disc, the maximum height in meters reached by the stone measured from the plane. So here's the plane that we're rolling on. This rock is going to fly off right there, and then we want to know how high it gets. So in general, even that one's fairly simple. We want to know what the vertical velocity is. Velocity in the y direction. If we knew that velocity in the y direction, hey, let's say it was just 10 meters per second. Okay, hell yeah. What do we know about gravity? Gravity is about 10 meters per second, and written like that, gravity is going to suck velocity, change in velocity by change in time. It's going to change your velocity by 10 meters per second every second. You know what I mean? It's good to write these equations kind of out, like in words, because then they just make so much sense. So if I have a vertical velocity of 10 meters per second, guess what's going to happen in 1 second? That's going to go from 10 to 0, because I'm going to change my velocity by 10 meters per second. Now, if this thing was getting flung down, you know what I mean? Hey, then in 1 second, I'm going, my vertical speed, Vy is down, and guess what? It's going to increase by 10 meters per second in 1 second. Whatever that vertical velocity was, it increased. But in this case, heck yeah, that 10 goes to 0, and that took 1 second. So now we can use that same approach. Let's say this was our problem, and we want to know how high we were going. So it's the same thing with the driving. If I was just had I just been driving or 10 meters per second, and I continued with that speed for 1 second, well, how far would I have gotten? And again, keep it simple. The units are the equation. We got meters per second and seconds over here. What do we do to these to get distance? We multiply them. And I would go a height of 10 meters. But we know this isn't the case because we started with a velocity of 10 meters per second, and then we ended with 0 meters per second. So it's the same thing as like, well, let's say at this stop sign, hey, we booked it. We're going 60 miles per hour, but over the course of the hour, I continuously slowed down to 0 miles per hour. And I want to know what my average speed is, but more importantly, how far I got. And we drove for an hour like this, 60 miles per hour, slowly and linearly decreasing our speed to 0. Our average speed is 30. We went 30 miles per hour. For 1 hour, we went 30 miles. So the same case here. I went from 10 meters per second to 0 meters per second. My average speed is 5 meters per second over that 1 second. Guess what? I went 5 meters. Heck yeah. So this can just really simply at least get you in the ballpark of what's going to be happening. So, and then again, we have to go back to, hey, what is that velocity tangential? Well, it's radians per second times what? Radius is something normal. That's velocity tangential. So we have omega r is velocity tangential, or velocity tangential is the radians per second times the radius. So heck yeah, we're already at an angle, and let's just guess, you know what I mean, if this is 60 degrees, we're at an angle of 50 degrees, you know what I mean? And we went for 2 seconds. They only want to go for 1.7. So, you know what I mean? Even like right now, we could just guess that we're at an angle of 45. That's a fairly safe guess. And that means, you know, with these angles, it's always good to remember, you know what I mean, sine of 0, sine of 30, sine of 45, sine of 60, and then sine of 90 degrees. Because if here's the angle, 45, I always do the sun is shining, and this is the sine and component. And what that means is whatever your hypotenuse is always the largest number in a right triangle. You know what I mean? You can't, I mean, no one's going to tell you that at the college level, but it's just like you need that repeated to you. It is the largest part because it is the vector that you're trying to find. It's the distance vector. It's the velocity vector. And then you want to know the parts of that. Well, we have a part this direction and a part that direction. It's always going to be smaller than that. And that's what sines and cosines do. They're always numbers between 0 and 1. They're fractions of that big one. Alright, so we have this is your sine component. And at 45, just think 007, 0.707. Sine of 30, that's easy. It's just half of that hypotenuse. It's 0.5. Sine of 0 is 0, because if we didn't have any angle, we wouldn't have any height. Sine of 90, if all we had was height, it's 1. You know what I mean? It's a multiple of whatever. It's 100%. And then sine 60, 0.866. I don't know how you're going to remember that one. I just think 85%. You know what I mean? So if you do have like a steep angle, here's your sine and component. This is 0.866. It's 86.6%. But at the end of the day, like, hey, this line is about equal to that line. This is at the point where you can almost say 0.866 is equal to 1. You know what I mean? There's a lot that you can do with that. You know, you can definitely guesstimate problems way faster if you're just like, hey, I have an angle that's 60. I'm just going to say that's equal to the hypotenuse, and that can go a long way in guessing strategy. So, booyah. So what do we have? A 45-degree angle, and that was just, hey, 007. And it's got to be 0.707. It can't be 0.77, because why would you include the 0? You know what I mean? So that's out. It can't be 007, because that just that makes no sense. And then so you just think 2 sevens, 007, you can't go wrong. And it's real accurate. You know what I mean? We'll go to degrees, sine 45. You know what I mean? It's 0.7071. You know what I mean? So it's super accurate. And even this, sine 60, it's 0.66025. So super accurate. You know what I mean? And you can do a lot with these. Alright, so, and where we're going with this is, well, I have no idea. But we just need the velocity component. We need the vertical component. Is that where I was going with it? I think so. But alright, so let's just say we have an angle of 45. And so whatever our tangential velocity is, we're going to... Oh, yeah, that's where I was going. You know what I mean? Hey, what's 007? Well, it's just 70%. You know, if you think sines and cosines are fractions of this hypotenuse, it's real easy to be like, hey, if I have like a 45-degree angle, and this is 100 units, my hypotenuse is the larger number, it's 100, you know what I mean? Hey, how big is this? And maybe that's not a very good one, you know what I mean? Sometimes 10. you know, if this is 10 units long, like how long is this? If you just guessed, is it 5? It's like, no, because that's 5. Alright, we're back. Heck yeah. So just even doing this guess and check process is like, is this 5? No, because like halfway is 5. You know what I mean? Hey, like, what's that? That's 7.5. Is that about right? I mean, now you're cooking. Heck yeah, this is about 7.5. You know what I mean? And in any guess, like 0.6, that would be a great guess. 8, that would be a great guess. Now if you said this was 10, well, maybe that's not a very good guess. You know what I mean? But if you have that 60-degree angle, let's do that 60-degree angle. So heck yeah, that's going to be a 60. We're going to call that 10. And at the end of the day, if you call this 10, like I'm gonna say that's cool. You know what I mean? Because if we throw this radius in there, hey, it comes to about there. That's pretty darn close. You know what I mean? It doesn't take an angle too much bigger to 60 to be like, nah, these are 10. So why I say this is 1, or equivalent to 1, is because this is about the last angle you could say that. You really can't say that with a 45-degree angle, that these are all 10s. But at a 60-degree angle, you'd be like, yeah, that's about 10. I mean, your hypotenuse, if the hypotenuse is 10, this side's about 10, and then move on with life. And this is 5, you know what I mean? Because it's, you know, because this is your 30 now. Sun is shining on the sine, and sine of 30 is 0.5. Okay, hell yeah. So that's triangles in a nutshell, and this really helps us guesstimate. So we're going to find that velocity tangential. Again, what is velocity tangential? It's that radians per second times radius to get that something normal. And so what was our final radians per second? Did we say we were going 5.6 radians per second? And wouldn't that make sense in two? Oh, interesting. Now let's go back. Let's take a pause. Because we said that our change in radians per second was 2/3 a radian every second. So in 1 second, we're going to go from 0 to 2/3 a radian per second. And in the next second, we're going to go 2/3 to 4/3. Is that not right? So right here we went 5/6 a radian, but now let's oh whoa. Yeah. So we already made our first mistake. You know what I mean? Radians are so difficult to work with. So this is radians, but it's not radians per second. So let's go back to that first second. We said, so that was a mistake. I apologize. So in the first second, we went from 0 to 2/3 a radian per second. And then we said our average velocity was 1/3 a radian per second. And we must have gone 1/3 radian. And then, hell yeah, make mistakes. You know what I mean? Because obviously, at the end of that first second, we're going 2/3 a radian per second. At the end of second 2, now we're going 4/3 a radian per second. So then the difference between the average velocity between 2/3 and 4/3, what I would do is I would turn this one into 4/6 a radian and this one into 8/6, and halfway between 4 and 6 is 6/6. So now we're going 1 radian per second on average for that 1 second. So we went 1/3 of a radian, and then we went, so here's radian number 2, split it up into 3s, and now we went a full radian. So now we're almost up here. We're not quite vertical, but we're pretty darn close. But that was in 2 seconds. Our problem says we're only going to go 1.7 seconds. So that's that in a nutshell. That was maybe just more playing around, but now I think we can actually just say, hey, where's the rock stuck to? A small stone is stuck to the disc. At time 0, it is at the contact point of the disc in the plane. Okay, so here is the rock. Oh, very interesting. I didn't even know where the rock was. Okay, so at t is equal to 0, it is at the stone is at the contact point of the disc and the plane. Cool, cool. So now, so here's our circle, and we're going to say, hey, this is, oh, this is kind of tricky. So now I have to divvy it this way, and then I have thirds. So there we go. And so now we got the gist of what radians is and the radian speed. Sorry for that hiccup, but now we'll get a little bit more accurate. So we have square root of pi for our time. It's 1.772 seconds. And so our change in radians per second per a change in second, this is equal to 2/3. Now you can use this as an equation as long as this is a constant number. You know what I mean? Like gravity. Like you can figure out, you know, if you jump off a cliff and you time the person that jumps and you're like, whoa, they were in the air for 1.7 seconds. Like that's very similar to our problem. And then gravity is 9.8 meters per second, and that's change in velocity, change in time. So you would take this and be like, well, I want to know their change in velocity. So just rearrange the equations. We have 9.8 times change in t, and then you would be like 9.8 times 1.7 seconds, and I should be showing units, but 9.8 meters per second, and if you write it this way, heck yeah, 1.7 seconds, seconds cancel, and now you're going to get the change in velocity, 9.8 times 1.7, and in 1.7 seconds of free fall, you're going 16.66 meters per second. I don't know anything about meters per second, but I know to multiply by 2.25. Just think times 2, but then 25% tip, and hell yeah, you're going 37 miles per hour. So that's very typical of a small cliff. You can be going 40 to 45 miles per hour for a big cliff. All right, so we can do the same thing with this equation. We want to find our change in radians per second. This is the equation. Again, this is an equation as long as this is a constant number and not some function of time or something, you know what I mean, or non-constant. All right, so we have 2/3 change in t, and we get 2/3 times 1.772, or 2/3 times the square root of pi. Square root of pi times 2 divided by 3, and we get. I'm going to store this as alpha w, and we get 1.18 radians per second. So now we got to keep track because we have a time change of 1.7 seconds. So we're going from velocity of 0, and I guess I like to say velocity because it's just kind of it's more sensical. But our omega right here at time 0 is 0 radians per second. And then at time 1.7 seconds, I'm just going to pick a spot, you know what I mean? Our velocity final is 1.18 radians per second. So now we want to know what our average, you know, we definitely need that average speed, that average radians per second. That's going to be 0 plus 1.18 divided by 2. Essentially just that. That divided by 2, and we get 0.59. I'm going to store that as alpha u. So radians per second. So this is our average radians per second. Same thing, synonymous with 0 to 60. And what's our average speed over the course of that hour? 30 miles per hour. We went 30 miles. So now we went 0.259 radians per second. But we didn't just travel for a second. If we just traveled for 1 second, we would go but we didn't. We traveled this speed for 1.772. And again, radians per second is the units on that. Time is the units on this. What do we do to get that distance? We just multiply. And so we get this alpha u of 0.59 radians per second times our time, which is square root of pi. And we get a total distance, you know, in an angular distance of 1.04 radians. So now what we know is that these are about 60 degrees. So 0, 60, 60, and then 180. So we're about right there. So just at the end of the day, we have a this is 60. Oh, holy, this is going to wig me out. This is going to wig me out, because tangentially, if we were right here, we were going 90. If we're, you know, so let's draw a bigger circle. Kind of a sloppy one. But, so if we're right here, tangentially, we're going 0 degrees. If we're right here, heck yeah, our angle is 90 degrees. And if we're like right at 45, you know what I mean, our angle is 45 degrees. And so yeah, because I was just, so if doing this helps you, because hey, if I'm at an angle of 60, like what's this angle? You know what I mean? Well, it's just 60. You know what I mean? Because if I'm here, my angle is increasing past 45, so it has to be 60. I just had to do that. I'm not going to spend too much more time proving that. That's all I want. I just wanted a simple representation to know that if I'm at a 60-degree angle, because now we're going to have a velocity tangential component, we're at a 60-degree angle, and then booyah, we can totally right now guess that, hey, like our velocity tangential is 1, you know what I mean? So even right now we can say, what's our angular speed at this time? It was this. This is our angular speed, because we were going 2/3 a radian per. I mean 2/3 times square root of pi. Yep. So we're going 1.18 radians per second. So now we can just do a quick guess, because we have, but what's our radians? It's 1 meter. So, so what we say, radians per second times radius is something normal, and that's our tangential velocity. So our tangential velocity is 1.18 radians per second times 1 meter. Oh, well, that's pretty easy. It's just 1.18 meters per second. So now we have the effect of gravity on this, and so we're only going 1.8 meter per second. If we were going 10 meters per second, hey, we would, our velocity would change by 10 meters per second in 1 second, because that's gravity. But now our change, so we can still do this. Let's just average it. We're going 1 meter per second. So how many seconds is it going to take to change our velocity from 1 to 0? Because gravity can do it. Gravity can change our velocity by 10 meters per second in 1 second. So just by comparison, it's going to take 1/10 of a second. So it's just really good to get some guess and check approaches so you don't mistakenly multiply numbers that are wrong. So now we only have 1/10 of a second. We're going to go from 1 meter per second to 0 meters per second in 1/10 of a second. Our average speed here is 0.5 meters per second, and we did that in 1/10 of a second. So now, if we have meters per second, again, units here, and seconds, what do we do to get distance? We multiply. So we have 0.5 meters per second times 0.1 seconds, and this gives us a fairly decent representation of how high we are going to get from this launch point right there. You know what I mean? So, and that's just good to know. If I didn't do this, I might have mistaken the answer that I got here to be the answer they're asking for. And that's not true. They're not saying from here, what's the height, you know what I mean? Because we're going to do like we'll model this with, and you'll see that in a second. But basically, this height was 0.5 times 0.1. This height was 0.05 meters, which times 40. It was, oh yeah, it only went 2 inches. But you can see that we're already at 60 degrees, and so what is this height off the ground? Because now if we have draw our circle better. If this is 1 meter off the ground, just guess what this is. You know what I mean? And again, this is about 1 meter. You know what I mean? We're doing that same guesstimation, that 60 degrees is about the same. Cool. I mean, but obviously we're at 0.86 meters, and we're only increasing. Yeah, our velocity's pretty low. So the stone detaches itself and flies off tangentially from the disc. Alright, so now we got our first kind of guess. We're going to grab a new sheet of paper, and then we'll start in on kind of, you know, going over this and trying to get like the correct answer. Cool, stone's right there, halfway, and then there and there. Again, alpha, change in W, change in T. We can rearrange this. This is the equation. We want to find change in W. That's alpha, change in T. And then once we find the change in W, we'll have, that's going to be our change. We're going to go from 0 to change in W. And then so our average speed, so we got omega average is change in W divided by 2. And once we get that, then we're going to multiply by our time. Our time is square root of pi. So our distance traveled, our angular distance traveled, like change in angular distance is going to be omega average times time. You know what I mean? So this is the cool thing, is like once you've played around with kind of the logistics of the problem, then you can go back and kind of put the numerical numbers on. And then the next time you do it with just the letters, it'll just be that much faster, and you'll kind of understand what it all means. So cool. So now we have our rate change in angle, and once we know that change in angle, and here's our angle, and that's fascinating. Yeah, 0 degrees is, so yeah, so this angle right here will be the same, and I kind of want to figure that out. So like this angle is going to be the same as that angle. So I'm gonna see if I can figure that out in 2 seconds, but I don't think so. For whatever reason, that's tricky to me. If we draw a vertical, you know, if you draw vertical lines, then this angle is the same as this angle, and then this is a 90. So I always do like, hey, if this is theta, and this is a 90-degree angle, this is phi. Cool, so that's 90. And then by, whoa. So if this is phi, then this is phi. And this is another 90-degree angle, so this has to be theta. And then if this is theta, and this is a 90-degree angle, this has to be phi. And then if this is phi, this is another 90-degree angle, this has to be theta. Yeah, that could be a whole video on like, you know what I mean, hey, trying to figure out what the angle is, especially when they're close. That's why I went back to just drawing and be like, hey, if this is tangential, this is 0, this is 90, and then do the 45, and that's obviously a 45-degree angle at 45, but we're at 60, so that's going to be a 60-degree angle. And then from that angle, we're going to have a velocity tangential that will have a vertical component and also a horizontal component. And we want to know the vertical component. So Vy, if this is my angle, it's going to be the sun is shining on the sinin. There's going to be that tangential velocity, sine of theta. Okay, and then once I get that tangential velocity, then I can, I really don't, I just actually want to say, hey, that is going to be my velocity in the vertical direction. And so the time to change, so we're going to say acceleration, gravity, the acceleration of gravity, acceleration, definition of acceleration is change in velocity, change in time. So this is the equation. So acceleration of gravity is 9.8 meters per second per second, and that's equal to change in velocity, change in time. What I want to know is the change in time to go from Vy to 0. And again, we already did that. If we're only going like and did we do that right? Yeah, we were going like 1 meter per second. You know, that was our speed of our rock upward. And so it's only going to take 1/10 of a second. And how would we find that? Well, we rearrange for change in time, and then we do change in velocity divided by 9.8. And I'm going to say G is 9.8 and get more letters on this. Now we have change in time is change in velocity divided by G. And change in tangential velocity, we're going from max to 0. So this change in velocity is just Vy. So we have change in time is Vy divided by G. And then once we get that change in time, then we know, then we can figure out the distance. You know what I mean? Hey, the distance that we got, because we know our velocity average. Our velocity average for that distance is going to be Vy. I mean, we went from Vy, that's our max upward velocity, to 0. Velocity equal to 0. So it's the same thing with that, hey, going 0 to 60, increasing your speed. Our average velocity is 30. So heck yeah. So our average velocity is going to be Vy divided by 2. This is our average velocity, and then we have meters per second, and then we have that change in t, which is in seconds, and that gives us our distance. So the distance, vertical distance from that location is going to be the velocity average, Vy times this change in t. So now we can really throw it all together. But our final equation has to be, hey, this d plus whatever height we're already at. So if we're on this circle and we get to this angle, then you know, let's draw. Well, no, I'll just do it right here. So heck yeah, this is our right triangle. The hypotenuse is the radius. That's the larger number. We have the angle that we got to. You know what I mean? Our change in angle is that. Here's the sine component. Do we want to know that one? No, we want to know the vertical component. That's what we're interested in. And but we actually just want to know oh, and this is interesting. I have to draw this one more time, because if we have a circle and we're at a 60 degrees, there you go. Yeah. This is 1 meter, and here's our 60, and so here's our we're doing the cosine of 60. Well, that's just 0.5. I know this is drawn horrible. But this should be identical to halfway. So if we do get to 60 degrees, so we're right there at 60, this is the halfway point. Heck yeah. So just in general, our problem should be 0.5 meters plus whatever extra distance. We didn't think that was very much, so it's like 0.55 meters total, 0.55 times 1,000 millimeters divided by 25.4. So we're like 21.65 inches off the ground. But the take-home point is 0.05 times 1,000 divided by 25.4. It really only launched 2 inches from its from the point that it detached. It really didn't go very high. Okay, so but we do want to get there with letters. So we want to find, we actually want to find this distance, which I'm going to call, for lack of creativity, just d prime. So the final height is going to be this d prime plus d, and that's it. You know what I mean? That's going to be the equation. What is this d prime? Well, we said if this is the sun is shining on this side, the sine component, this is your cosine. And what the hell did we just say? We said the larger number, the hypotenuse, times the cosine. Cosine's always a number between 0 and 1. So we're going to take the larger number times the cosine of the angle, and that is that distance. So heck yeah. And but we don't want that distance, we want this one. So this whole thing is the radius. So this distance, d prime, is the radius minus r cosine theta. So there you go. This comes up a lot. You know, you might see this. R minus r cosine theta is, yeah, because you don't want that distance, but you want that one. So you take the whole thing and then subtract that to get that one. Cool. So we're going to have h is r minus r cosine theta. And then we're going to add it to our distance, which is Vy divided by 2, change in t. Okay, and then even this theta, this theta is change in theta, which is omega average t. And we already see that omega average t is change in omega divided by 2 t. Cool. And what's change in omega? Well, that's alpha change in t. So let's do that one. So we can say change in omega is alpha change in t divided by 2, and this is also change in t. So, and we're just going to say change in t is equal to t, which is equal to the square root of pi. So we have alpha is alpha t divided by 2, and then we're going to multiply it by t again. So change in alpha is alpha t squared divided by 2. Now again, you don't have to do what I'm doing and going straight to letters. You could have just solved it piecewise, getting those, but we already did that. We already did that with our guess and check. You know, we already have some sort of idea. We don't need to do that with the real answers. We can do that at the end to like have a double check. Okay, so here's our changing out. Because even right now, it's just like, I don't know. I might have made a mistake, and then that's totally not true. But you can see how this is like very similar. Like, hey, this looks like distance. Distance equation is acceleration divided by 2 t squared plus, you know what I mean, some initial velocity to the t plus some initial angle that you already started with. Well, we're just going to say, hey, we started at 0 angle. We didn't have an initial velocity. So now, like, if you're you know, kind of paying attention to the equations, you're just like, heck yeah, we didn't make any mistakes. All right, booyah. And so that's going to be our change in angle, which is our velocity average, which is that divided by 2 times t. And then that change in omega is, so we got that. So now we have change in angle, and that can go right in there. So now this is just the inputs, you know, our t. That's what we give, and then our angular acceleration. All right, hell yeah. So now for this Vy, so this change in t is just t, cool. Now this Vy, what's that? That's the velocity tangential sine of the angle. The angle is change in angle, and we got that. Now the velocity tangential is the change in omega, that final omega, because omega final is just change in omega, because there's no omega initial, there's no initial radians per second, there's no initial radial velocity, and so what did we say velocity tangential is? Radians per second times radius gives you something normal. All right, so velocity tangential is change in radians, which is just the radians final, times radius. Cool. So let's write this. Vy is equal to change in omega times radius, and then sine of the angle. But now we're saying that here's change in omega. So velocity in the y is alpha t times the radius, sine, and then the angle, is alpha t squared divided by 2. All right, heck yeah. Now we're cooking. So now we have, and then we have this Vy. All right, booyah. But we need to define this D. So this D goes right in there. It has this Vy. Vy divided by 2 times T. Heck yeah. So this is in the sign. This is the sign of the angle. But we do have another T here. So Vy divided by 2 times T. You're just going to divide this by 2 times T. All right, let's get the final equation. H is D prime. It's going to be R minus R cosine alpha t squared divided by 2. Booyah. Plus Vy divided by 2t, which is 1/2 alpha t squared r sine alpha t squared divided by 2. Booyah. And that's it. Our time is there. Our alpha is there. Time alpha. Time alpha. Time, and alpha is angular acceleration. And then we have our input as the radius. Alright, so I guess I don't have any more sheets of paper. Might as well just fold this one in half. And so we're going to have H is equal to, I'm just going to rewrite it. And it is good to get used to letters, you know, I mean, you're going to make a ton of mistakes, though, just using letters, probably. But I don't know. That's why I did the guess and check process. But we got 1 meter minus 1 meter cosine. Alpha is 2/3 radians per second. And then time is pi, a square root of pi seconds. But we're squaring that, so we get seconds squared divided by 2, and that is in the cosine. Now we have plus 1/2 2/3 radians per second squared. I'm just going to do that. And then time is square root of pi seconds. That's all squared, though. So then we have 1 meter, and then we have sine 2/3 radians per second squared, square root of pi seconds, but that's squared, divided by 2. So we can really clean this up. We have H is 1 meter minus 1 meter cosine. This is just pi, and so we're going to have the seconds will all cancel. And then you're just going to have radians. And that's good because radians is dimensionless. And then so if you're going to find the cosine of, radians is an angle. So sorry. It's an angle. So we're going to take the cosine of that. Oh, and that's a good check on reality. I got to be in radians. So booyah. So now I'm in radians, and so I'm not going to get messed up there. And we're going to have 2/3. Now dividing by 2 is the same thing as multiplying by 1/2. So multiplying by 1/2, I would get 2/6. And does that make sense? 2/3 divided by 2 is 2/6. So yeah, so cool. So I get 2/6, and then square root of pi squared is just pi. So 2 pi 6, and that's just 1/3 pi thirds. So we got pi divided by 3 for the cosine. And for sure, I mean, this is a problem where you should be like, hey, there's pi. I mean, if this is 0, there's pi. Here's 2 pi. There's pi divided by 2. And, you know what I mean? So, so there's 1/3 of a, I apologize. But yeah. So there's pi divided by 3. Pi divided. So we were totally spot on that it was a 60-degree angle. So we got to a 60 degrees. So so we can just do cosine of pi divided by 3, and it's 0.5, and that's what we would expect. Yeah, 1 meter minus 0.5 meters, and then we can kind of go back to our problem. Yeah, now I'm right down here. And heck yeah, exactly what we said. At 60 degrees, this is half a meter. Okay, so now we can just really start cleaning it up. We're going to have 1 minus a half, so we just have 0.5 meters plus. And now this stuff, you know what I mean? Seconds get squared, so seconds cancel. So we'll get this out of the way. So we have radians. Yep, so we have the dimensionless radians times meters, and so this just becomes meters. Cool. And then we multiply by the angle. And anytime you're multiplying by like the sine of an angle, hey, this is your hypotenuse. You know what I mean? This is your larger number, and then you're multiplying it by that fraction of the whole. All right, heck yeah. And so this is going to be pi. 2/3 divided by 2 is just 1/3. So we got pi divided by 3. And then we have sine of, this is going to be pi. And then we have 2/3. And then so again, we just have pi divided by 3. Sine of pi divided by 3 is sine of 60. And so now we're up here. Here's our angle of pi thirds. It's sine of 60. That's 0.866. Even from earlier on, hey, this is just 1. You know what I mean? So technically, you're just going to have increase by pi divided by 3 meters. And maybe I was off on that. Pi divided by 3. Oh, this is fascinating. I think I was off on my initial guess. We'll have to go back and see why that's the case. But yeah. So if I do this, in this bracket is the square root of pi squared. Whoa. Square root of pi squared. Obviously, that's just pi. And then times 2 divided by 3 divided by 2. And that's just pi divided by 3. Heck yeah. And the sine of that is 0.866 times square root of pi times 2/3 divided by 2. Oh, whoa. So I guess I got 0.5. Whoa, was I off on my initial guess? You know what I mean? Like our omega, I need to go back on that. So our omega was 1.18 radians per second, our max velocity. And we were just going to assume that was straight up. Velocity y was 1.18 radians per second. Radians times radius is the velocity tangential, and that's going to be 1.18 meters per second. Now gravity is going to affect this by 10 meters per second every second. So it's only going to take 10 divided by that. It's only going to, alpha W, alpha. So let's do this. Gravity is change in velocity, change in time. I want to find the change in time. I'm going to say that's change in velocity divided by gravity. So we're going to have alpha W, 1.18 meters per second divided by 9.8. This is the change in time. So, so that means that we went from this to 0 meters per second. Our average velocity is omega divided by 2. So we went for 0.59. We have a velocity of 0.59 meters per second. And we went for a total of So yeah, like I'm getting 0.07 meters per second. So I don't know why this got messed up and isn't representative of that. So we definitely, I think it's oh shoot. Where would we have gone wrong? So this is 0.5 times 2 divided by 3 times square root, or just times pi. Alright, hell yeah. So I dig finding mistakes, you know what I mean? It's really fun. So what happened here is I said, you know, in this equation, one of these times was squared. Well, that's not the case, because in that scenario that I just showed you, we had to multiply by the time that was due to that average velocity divided by gravity. And then we just assumed, our mistake was just assuming this time was square root of pi in both scenarios. So if we go back to where this came in, our average, we took the tangential velocity and we got the component, the Vy component. And then once we found that, we said, hey, that Vy component went from Vy to 0. So we got an average velocity of Vy divided by 2. And then once we got that, but this time was a different thing. Oh no, it can, yeah, we got that average velocity, but then we had to multiply it by the time that it went from max to 0. You know what I mean? And so how we got that was we just took that initial velocity in the y direction. And we said, hey, acceleration of gravity is change in velocity, change in t. Now this is the equation. You're like, hey, gravity, change in velocity, change in t. There's 3 things here. I can rearrange them. I'm going to rearrange for change in time. So I'm going to say that's change in velocity g. The change in velocity is Vy because it goes from Vy to 0. That's the change. And then so, heck yeah, there's our change in there's our time term, Vy divided by g. And Vy is Vt sine theta divided by g. So we can say time is Vt sine theta divided by g. But this time component then comes in right here. So we say distance is Vy divided by 2 times change in t, which is I don't want to get, this is Vy sine theta. So so we have Vy sine theta divided by g, and so we have 2 Vy's. Oh yeah, I feel like that's getting redundant, but yeah, our distance is Vy squared divided by 2 sine theta divided by g, because this was our time term, Vy divided by g. Yeah, I think I need to slow down just a little bit. So we have our time is Vy divided by g, and then we have this equation over here for our distance is Vy divided by 2t. Yeah, it's that simple, right? Vy divided by g is t, and then this is our distance is Vy divided by 2t. Yeah, I don't know why I had to make that so complex. Cool. So now we have we throw this right into there, and we get Vy squared divided by 2g. Heck yeah. So that's going to be our distance for this equation. And again, this is h is equal to d prime plus d. So this is the d that we're solving for, and we get and how did I find the d? I just said it was Vy divided by 2 change in t, and then I just messed up that t part. So yeah, oh okay, yeah. So this whole distance equation is just a function of the time in the air, the projectile time due to gravity. At this point, it has nothing to do with man. So I'm gonna call this T prime. Well, I called this D prime. Yeah. So I'm gonna call this initial T prime, and then the time in the air just T. So that'll hopefully make sense. So now for this is T prime squared, and this term right here for our distance. Holy Toledo! I apologize for. Yeah. We can totally get rid of that and just say, hey, that distance is just Vy squared divided by 2g. But Vy is the tangential velocity sine theta. So we're going to have V tangential squared sine theta squared divided by 2g. And sure, this theta is change in theta, and then we have that as, W average t. W average t is the omega divided by 2t, and omega is alpha t. So we do get that. We do get that 1/2 alpha t. And remember, we can just know this because it's very similar to position equation for projectiles is 1/2 the acceleration t squared. And so that is going to be holy Toledo. Oh yeah. So the change in angle. That's interesting. The change in angle is synonymous with change in position. The position equation is 1/2 alpha acceleration t squared, where the theta equation, and this is theta as a position of theta as an equation of theta as a function of time is 1/2 alpha t squared. So that's kind of cool that we kind of learn that process without a textbook just saying so. You know what I mean? So I definitely appreciate that. And then for that angle, so we're gonna have this distance is velocity tangent squared sine squared, and then that alpha is just 1/2. I mean, this theta is just 1/2 alpha t squared, and then this t. Yes, this t will be that t prime. That the t prime is going to be the square root of pi. So now we're just good to go on that. We're going to divide that by 2g. Also, velocity tangential. Well, what the hell is that? Well, again, that's radians times radius. And where did we get the radians? Well, that's going to be angular acceleration times the time. And this is t prime. That's the square root of pi. So there you go. So this is radians. So alpha t prime r is velocity tangential. And isn't that what we have somewhere? That alpha t prime r. I've got oh man, yeah. Well, let's look for that one. Yeah, we're getting a little bit sloppy here. But yeah, we can say that the change in the angular velocity alpha times t, cool, and then so that's going to be our max at that point, and we have that in our calculator as alpha w. And then so the actual velocity tangent, I'm just surprised that I don't have vt on here. I just don't know where that would be. But yeah, just right here, we just said, hey, VT is that change in omega times the radius. So there you go. So yeah, so VT is alpha T, that's omega, times the radius. Alright, my camera stopped and I just kept on talking, but man, okay, now we're going to bring it home, you know what I mean? Because we basically know the whole problem set up, and what we want to find is want to find that maximum height as a function of all our input parameters, our radius. We want to find it as a function of this input parameter, angular acceleration, and then of our t prime. And that's going to be our square root of pi over theta. Heck yeah. And I guess we're going to have, there's more, function of gravity, and we'll find out whatever. And again, we have the equation of d prime plus d. I'm going to say that this t prime is square root of pi. And we got to a 60-degree angle. And so we're going to say, hey, that's what are we calling this? We're saying that's that d prime at the angle that we got. This angle we're going to say is change in angle. And we have angular, at the point that it detaches, we'll have angular acceleration final. We start with, angular velocity. I should just call it velocity. You know, I mean, we start with an initial velocity of 0 radians per second, and over that course of our change in t prime, or just t prime, we increase. So the first thing that we do is we find our change in omega, which is our angular acceleration times our t prime. We know that this change in omega is just omega final. So then we can find our velocity tangential, which is that change in omega times the radius. So this just becomes alpha t prime r. This is our velocity tangential. We're going to find the y component. Vy is velocity tangential sine of the angle. But what angle did we get to? How did we find that? Yeah. We said that if we started at 0 and then got up to this change in w, then our speed average, our radial speed in radians per second, is going to be our change in omega divided by 2, which is alpha t prime divided by 2. Okay, and that's going to be our average speed, and then over the course of that time will be our distance. So then our distance, our change in omega, will be 1/2 alpha t prime squared. And you can see this is very synonymous with a position equation, which would be, due to any sort of, I'm just thinking like due to gravity, you know what I mean? That's an acceleration, and your position equation is 1/2 the acceleration of gravity t squared. Plus maybe an initial velocity times t plus an initial position, but we don't have any initial velocity and our initial position is 0. So this is totally understandably a function of that angle. Okay, so then that actually just goes right into here. So now our Vy is velocity tangential sine of 1/2 alpha t prime squared. But again, what's our velocity tangential? That's going to be this. So our v prime becomes alpha t prime r, and then we got sine 1/2 alpha t prime squared. And that was all just to get the velocity in the y. And then we said, well, if we do have velocity in the y, hey, gravity is 9.8 meters per second squared. And what's that? That's change in velocity, change in t. And then so we have an equation for the change in time. So change in time is change in velocity divided by gravity. And then our change in velocity will be this Vy to some point V0. You know what I mean? We're gonna stall, and that's gonna be our max height. So we want to find this, and we're gonna call this D. This was D prime. And at the end of the day, it was just half. Our angle was 60, cool, and our radius is 1, so D prime at the end of the day is 0.5 meters. But here's an equation. So our equation for D prime is going to be also that, hey, that radius minus r, so this is also our hypotenuse cosine of the angle. So heck yeah. So we're going to take this full length minus r cosine theta to get D prime. So this is going to be r minus r cosine theta, where theta, again, is this. So we're going to have height is equal to D prime plus D, and that's going to be r minus r cosine of 1/2 alpha t prime squared. Cool. And then plus D. And that's the next thing we're trying to find. What's the distance that the rock gets thrown into the air? Well, we have our initial velocity. It's going to go from that to 0. And so that's going to be our change in velocity. So our time to do that is our change in velocity divided by gravity, which is Vy divided by g. And this t is going to be just t naught prime. And then once we find that time, we can say our velocity average for that is Vy divided by 2. And then so we can find the distance d by taking the velocity average times that time. And this is where kind of the time component comes up twice. So d is going to be V average, which is Vy divided by 2. And then our time is going to be Vy divided by g. And we get Vy squared divided by 2g. So that is our distance as a function of Vy squared. But we do know that Vy is equal to Vt sine theta. And we know that Vy is this. So there you go. We're going to square this and then divide by 2g. So at the end of the day, d is this squared divided by 2g. So let's write the whole equation. We have h is equal to r minus r cosine 1/2 alpha t prime squared. But you see how we did the guess and check, got an answer, used the equations once, for very, very, very nice numbers that we could keep our head wrapped around. And now we're going to try to go back and put the letters to it, you know what I mean? And right now, this makes sense to me. I have 1/2 alpha t prime squared. Hey, this looks like that position equation, and it's the position of the angle, you know what I mean? So this is an equation for where the angle is at any given time, you know what I mean? So right there, that's an equation for theta as a function of time, and I can see that. I can see that this r minus r cosine theta is just the total distance minus the cosine part. So now that gives me this remainder distance, and that's going to be, hey, this initial height. And again, the question says, what's the height of the rock from this horizontal plane? Well, you're going to have that distance. Cool. And then plus the height that the rock gets flown up into the air. And again, it's really good to do that by what's the initial velocity, and then it's going to go to 0. That's a change in velocity. Gravity makes that change in velocity happen over a certain amount of time. And then the average velocity from that Vy to 0 is just Vy divided by 2. times that time, that average velocity times time, is going to be that distance. And it goes back to, hey, going from 0 miles per hour and then slowly increasing to 60 miles per hour over the course of 1 hour, our average speed is 30 miles per hour. This comes up a lot, and this is why you just do the integration approach, but it's kind of cool to do that visual approach. Alright, so heck yeah. So this d term is going to be Vy squared, all this squared divided by 2g, and we can just write it. So we got, yeah. So I'm going to write alpha squared t prime squared r squared. I'm going to write it like that, that I'm comfortable with that. Sine squared 1/2 alpha t prime squared. Oh, yeah, it got divided by 2g. And we already ran this in our calculator, and we got that value of 0.05. So at the end of the day, we got 0.5 plus 0.05 and times 1,000 divided by 25.4. I don't know. So in American, we're 21.79 inches from off the ground. That rock is off the ground by 27.9 inches. You know what I mean? This whole wheel is 2 times 1,000 divided by 25.4. The whole wheel is 78.74 inches in height. You know what I mean? So so that divided. So you're more than a quarter up the circle. You know what I mean? So yeah, that 0.5 is a quarter of the way, and then you get just a little bit farther. You know what I mean? The rock does not get thrown into the air very far, and I think I'm pretty satisfied with my assessment. You know what I mean? Definitely using the radians per second. That's the take-home point. Like, what is? Let's go back to this. 2/3. So we got 2 divided by 3 radians, a change in velocity every second. So cool. We're gonna go 0.6 radians a second. And our tangential velocity is just radians per second times radius. So and our radius is 1 meter. So we're going 0.6 meters per second. You know what I mean? And so we're not going very fast. Now, if we were increasing this, if we did a couple revolutions, sure, we'd be going hella, and then it might fly off and get really high. But yeah, at the end of the day, we aren't going very fast. And we said we're going to do that twice. So our max speed is 1.3 radians per second, or 1.3 meters per second. And again, gravity is changes that velocity by 10 meters per second every second. So it's only 1/10 of a second of hang time, with an average velocity of 0.5, which is 0.05. So even just doing that, those 3 steps just really hone in what's happening, even when the equations get really complex. Okay, so here we go. So now we can just write the final equation. So we have 1 plus 1 cosine 1/2 2/3. This is square root of pi squared. I'm just gonna say pi plus 2/3 squared pi, you know, because it's square root of pi squared, 1 squared sine squared 1/2 2/3 pi divided by 2 times 9.8. So again, this is just pi divided by 3. This is sine of 60, and it'd be sine of 60 squared. So it'd be 0.866 squared, which is 0.75. You know what I mean? Sine of pi divided by 3. That's a good one to know. You know, if you square this 0.866, which you should memorize is sine of 60, you get 0.75. So cool. So this really simplifies to 1 plus 0.5 plus, well, at least this goes to 0.75. But yeah, we'll have, this goes to 4/9, so we'll have 4 pi, this is 3/4, so we're going to go 3, we're going to have 9, I'm going to do that fourths, 2, and then 9.8. So the 4's can cancel, the 3 can cancel with the 9 to get 3, and then we get pi divided by 6 times 9.8. Okay, and then so pi divided by 6 divided by 9.8, heck yeah, it is that term, 0.053. And then plus 1, oh, see, this is a minus. I got in trouble there. You know what I mean? So at the end of the day, this is just 0.5. So that plus 0.5. Heck yeah. And I guess our h is 0.553 meters. And I don't know how if they wanted, maximum height in meters reached by the stone. So final answer, 0.553. You know what I mean? We beat this one with a fork. And heck yeah, but we do have an equation. You know what I mean? So you would say this is an equation of height as a function of radius, as a function of angular velocity, as a function of time, time for the thing to rotate. You know, t prime. It's a function of and a function of gravity. All right, and that should do it. You know what I mean? So there you go. We got a function of h as a function of those 4 things, all in letter form. And now we can manipulate the problem as much as we want. The only thing that we can't do with this problem is start with an initial angular velocity of anything but 0. You know what I mean? The rock has to be in this location as well as the angular velocity. So that's interesting, you know what I mean? The second thing to do would be like, hey, can we make an equation where the rock can start at any angle, you know what I mean? So theta is whatever. And we would start this, we would say the angle 0 is right here, but the rock could start there, and it could start with an initial radians per second, and then have that angular acceleration. So this equation does not satisfy that scenario, and that would be the better one to do. That would be a better problem. That would be a more advanced problem, just like, hey, come up with an equation for the height, but then you'd run into issues where maybe the rock is at a point where it's actually getting thrown downward. So then the max height is just the point that it detaches. You know what I mean? So, yep. But anyway, I think I'm going to be done with this one. But we do have to go online and see what the answer was. I have not looked this one up. Alright, so catch you on the flip side. Alright, heck yeah. So I just looked up the answer, and so we're wrong. You know what I mean? But we're not wrong by much. You know, and that's good. Because the huge red flag that I should have picked up from the beginning, I mean, then at the very start of this whole thing, didn't we say, hey, if we have something rolling, it's going to have an omega, which is going to cause a tangential velocity, but then this thing is rolling. And so it itself is going to have a velocity. So you're going to have, so at any point, you know what I mean? So if this is the velocity of it, you're going to have, hey, the tangential, you're going to have the velocity tangent. If you're at the top, which is the omega r, that's going to be your velocity tangent. Of just a rotating disk, but the fact that the disk is now rotating too, you're going to have to add that to it. So I did not realize that. And then so in our situation where we have this disk rotating this way to the left, when this thing is released and has a tangential velocity in that direction, well, it also has a component this way. So well, it seems like that would no, it seems like we should have been fine. Oh, this is fascinating to me. Because all we wanted to know was the height above the ground. Oh, this is killing me, because that's the only thing we're concerned with is the velocity and the y component. Because the velocity and the y component is the only component that can generate any height. It won't have anything to do with the fact that the circle is moving sideways. So I'm actually, well, let's go over the solution and see if we can. I mean, that's half the battle. It's like, can you actually take someone's solution and understand it? So here is so they're using a value of g of 10 meters per second. And maybe it's that. Maybe I am 100% right. They just used a different value of g. So at the end of the day, we got 0.5, and we're going to have, oh yeah, that is right. You know what I mean? Because they got an answer of pi divided by 6, and because so let's see, we have 0.5 plus pi divided by 6 divided by 10. Nope, that's going to give us a bigger answer. Okay, well let's see what they did. This will be fascinating. But the cool thing is heck yeah, they do have this equation for theta. So this is so fascinating to me. So if our angular acceleration is 2/3, the definition of angular acceleration is the same thing as the definition of acceleration, being change of velocity, change in t. This is change in omega, change in angular velocity, change in t. Now this is the equation. Or you can say it's dw dt, and then you can separate variables. So now we're going to have dw dt is equal to 2/3, and then dw is equal to 2/3 dt, or dw is equal to alpha dt, and then we can integrate to get omega, or angular velocity, is alpha t plus angular velocity initial. You know what I mean? And then the same thing, we can say angular velocity is change in radians, change in time. And then separate variables, we get d theta is equal to w dt, integrate, and we get an equation for the angle as a function of time is 1/2 alpha t squared plus the initial radians per second squared plus the initial position, theta initial. So heck yeah, this is what you would get also plus theta initial. That's the only thing that's missing on here. But they're just taking theta initial to be 0. But the initial theta naught is also 0, and then so you just get 1/2, 2/3, and then square root of pi. So yeah, you get that pi third radians, which we know is an angle of 60 degrees. And then so cool. And then the angular velocity of the disk is well didn't we find that equation? Angular velocity of the disk. Yeah, so that was the position. That's cool. But we also have an equation for angular velocity of the disk. It's the initial plus the AT. And if you write it, it's better if you write it like this, because it just matches the integration. When you write it backwards like that, I don't know if it's considered backwards. It's just a little bit more confusing, because you wouldn't do the integration that way. You would have the 1/2 AT squared first, and then the initial angular velocity second. Okay, but then we get 2 square roots of pi third radians. Now is that what I got? Yeah, because we had 2/3. This was the angular acceleration times the time, which is square root of pi. So that is our change in omega. You know, we definitely have that down pat. Now our velocity. Oh, they're saying the velocity of the center of mass. Is that what they're saying? Velocity of the center of mass? Maybe not. They do have this picture. Velocity of the center of mass. So if this thing is spinning this way, starting at the bottom, going up to here. They just drew it backwards. I spun it this way. They're spinning it this way. So yeah, so this thing's going this way, and so this whole thing is going that way. So if you get the, and if here's the center of the circle, and I guess, is this circle just bummed up? I was saying that's the center. That's kind of hard to see. But yeah, obviously the center of the circle, velocity, the center of mass. That might be the only part that I might be confused on. Is no, I don't think so. So if you have a circle and it's rotating and it's on the ground, the velocity is 0. It has, like, so if this thing's rolling this way with a certain speed, the speed is the center of the circle. The center, like if you're traveling on a bike, 2 wheels, it's the center of your wheel that's actually your linear speed. This portion of your wheel is fixed to the ground. It actually is not moving. And this is your velocity center times 2. You know what I mean? And then so, and then we just want to know if the wheel is just in space and it's spinning at the same speed. So like right now we have some sort of omega. And if we have some sort of omega, our velocity tangent at any point is just omega times r. And so what we're saying is that oh shoot, yeah, that is interesting. Like I'm kind of losing my track. But yeah, if you just have a wheel that's spinning the same speed as your bike, but it's not hitting the ground, the velocity of the wheel itself is omega times r. Huh. Yeah, I would think that the velocity of the center of mass is just half that then. Well, where am I getting that wrong? Because they're saying the velocity of the center of mass is omega r, just omega r. Oh, that's fascinating. Alright, so then let's move on. So they say, so at the moment it detaches the situation, then the velocity I'm going to take a pause and then kind of work through this. Alright, this was a trip. You know what I mean? I spent about 5 minutes looking this over and not too much more, so holy Toledo. Yeah, so what we learned 2 things. Like, my answer is 100% right. They just want this answer in such a weird way. They want the answer as 1/2 plus x divided by 10, and they want you to solve for the value of x. I've never seen that in a problem. I don't even know why that's useful or why that's functional. So down here, now I'm in degrees, but we got 1 minus cosine 60. Obviously, that's the 0.5 that's off the ground, but then we have plus pi divided by 60, and heck yeah, we get our answer of 0.552 or 0.55. Did I say it was 0.553? I'm not quite sure. But anyway, and then what they wanted in was this form. So then you're going to subtract 0.5, and then this is going to be equal to x divided by 10. So then you're going to multiply by 10 and get that. Divide by pi, and you get 1/6. So x is pi divided by 6. So now if you do 1 divided by 2 plus pi divided by 6, oh shoot. So 0.5 plus pi divided by 6 divided by 10. Heck yeah, you get that answer. Okay, so we're going to finish up by at least not messing this up. So if I have a bicycle wheel, it's laying down distance. You know what I mean? So the speed that I'm going is the speed that is getting laid down by the wheel itself. And so, so if I'm going, 30 miles per hour, shoot. Holy Toledo. So yes, so that is your speed that's getting laid down by the wheel. That's also the speed of the center of mass. But what we know about a wheel is that in relationship to the actual ground, is it's not moving. It's totally stationary at the contact point. So the only way that's possible, and I think of it like a stick. So if I have a stick that's at the contact point, has a center, and I'm saying that this is going 30 miles per hour, then heck yeah, this has to be going 60 miles per hour. And but then you take away the ground. I mean, this wheel is still spinning with that angular velocity, and then so we can say the velocity tangential is omega. So velocity tangential is omega r, and so that is the tangential velocity. So the tangential velocity again of the outside of that wheel is being laid down as linear distance. So that speed of the outside of the wheel is the speed that it's getting laid down. But it's also synonymous with the speed of the actual bike. Every molecule on the frame of that bike and attached to the center of that wheel is going that speed. So then it's very useful to take a wheel and say, forget about how it's circular, but it's just a stick where at any given moment in time, the speed of the contact point is 0, but the speed of the center of the hub is the speed of the bike is 30 miles per hour. And by geometry, you know what I mean? Hey, you have to have a continuity between every molecule here. So if this midpoint's going 30, the position on the ground's going 0, the top of that wheel is going 60 miles per hour. It's the speed of the wheel plus the speed of the bike. Cool. So that does, if you wanted the horizontal distance, if the rock got up to here and they said how far did it get flung forward before it hit the ground, then that would for sure be a function of the velocity in the x direction. But what they asked for is at any point it's going to kick off, and we took our value with just the velocity of the y direction. And that's the only thing that's going to be affected by gravity and reach some max height. And that's the height above the ground they're interested in. It doesn't matter if we're going light speed that direction. Obviously the wheel will be going really fast. But the speed of the wheel in the x direction, this direction, is irrelevant of the y component. That was the only component that we needed to know. So it didn't matter if this wheel was just spinning in the ground, on a stand where this wheel wasn't rolling across the ground. It's the same height in that case as if it was rolling across the ground. So yeah, the velocity in this direction is not affected by the height. But again, if you wanted an equation for the velocity for the max position that this thing got flown off, from the back end of the wheel. So let's say you're spinning this way, and then within 60 degrees it flies off. Maybe you want to figure out how far it landed from the location that it flew off. Or make the problem better and be like, hey, what's the position it lands in relation, and when it lands, where is the back of the wheel? Now the wheel's over here. So all of those are good questions to ask, and you could definitely get equations for them. All right, so heck yeah, so that was a pretty good understanding. But yeah, I get it. I get how, you know, watching someone else do a problem is just like I wouldn't, you know, I get some of it, and then you get to I don't know. I would have to make a separate video on like, oh yeah, I totally see exactly what's going on here with the vectors they're using. They have tangent of the angle, but I like my way better, and I'm glad I caught my error. And there was no error. It was just a bizarre way to answer the question, and I've never come across these JEE tests before. So hopefully we'll do more. And dang, sorry to make this a 2-hour video, or however long it took, but it was good. It was fun, and we learned a lot. And we definitely learned how we can, you know, model the problem in different ways. But the take-home point was this. It's so synonymous with... so now anytime that I see an angular acceleration, I know I can just say, hey, that's dw dt, separate variables and integrate. Get an equation for angular velocity, get an equation for theta as a function of time, angular velocity as a function of time, and then that's sweet. Okay, so thanks for joining me, and guess what? That's a video.